Hi there, and welcome to Raylene Math. In this video, we will take a look at transformations of curves and also defining curves by parametric equations. So let's graph the parabola y equals x squared. We start at the vertex 0, 0, then we go right or left 1, up 1 squared. Right or left 2, up 2 squared, which is 4. Right or left 3, up 3 squared, which is 9. That's really just making a table of values. And we get the parabola, which doesn't have any constant slope because this is a nonlinear function. And it looks something like that. Now we're going to use this parent graph to come up with this transformation, this change of it. And most people would say that we move 3 spaces to the right from the parent graph to get this red graph, and we move 1 space down. So every point on the graph will move according to this. And if we start with the vertex, that means the new vertex will be at 3, -1. And then there is no resizing or scaling, and there's no reflection of this graph, so we would continue going right or left 1, up 1, right or left 2, up 4, and then right or left 3, up 9. 4, 5, 6, 7, 8, 9, right in my way, and on the other side. And so we would come up with a transformation graph that looks like this. Trying to get it a bit tidy. And so we get a parabola that has been moved 3 over and 1 down. 3 to the right, I should specify. And so what's actually happening here is that we're getting a vector translation where the vector is actually 3i hat minus 1j hat according to the transformations. I, however, don't like to do transformations in this way because it doesn't allow us to grow. And don't you ever wonder why we do the opposite instruction for x, but we don't do the opposite for y? Let's try something different. What if we were to rewrite y plus 1 equal to x minus 3 in brackets squared? It's the same equation. Let's just take a look at what happens if we type the equation in this way. First of all, there's our blue graph, and there's our red graph. But what if we were to write the red graph as y plus 1 equals x minus 3 all squared? It's the same equation, and it's the same graph. If I turn off the red one, the purple one is there underneath it. So you might ask, well, why bother? We don't need to. But the reason why we bother is because we can't always isolate y. And now if you take a look at the instructions in purple, you do the opposite for x, you move 3 to the right, and you do the opposite for y, you move 1 down. And that consistency is something that's quite nice. We look for a lot of patterns in math. And so from this point of view, I would like to continue working with what I call transformational form, as opposed to function form where y is isolated. So this is transformational form, and from this perspective, we will always do the opposite, transformational. So this is one way of looking at it, and let's see why it might be useful. If we move on to the next curves, it's no longer a function because we have x squared and y squared, but this is our unit circle with a center at 0, 0 and a radius of 1. So from the center we move right or left 1, and we move up and down 1. And so inside this square of length 1, we would get a circle. And so that is our unit circle. Now, when we take a look at the equation of the red circle, we can see that every point is going to be translated 3 to the right and 1 down by that same vector, including the center. So the red circle is going to have a center located at +3, -1. Because if I pick up this vector might not work over here because I might not have the same scale. That's pretty close. And so my new center is going to be over here at 3, -1. And I haven't resized the circle, so I still have a radius of 1. So I go right, left, up and down 1. And so that gives me my new circle in red. And I can see now, without being able to isolate the y-coordinate because of the presence of the exponent 2, which occurs if I don't have a function, let's say, I don't actually need to do the opposite for x, but not the opposite for y. So let's take a look at this green equation. It looks quite similar to the red one, but we have a denominator in it. So let's rewrite it first as x minus 3 all squared over 9 plus y plus 1 all squared over 9 equal to 1. And if we multiply both sides of the equation by 9, we can get rid of the denominator, and that gives us an equation that looks a lot like Pythagorean theorem. And this Pythagorean theorem equation is really what's happening when we get a circle. And so we get a base squared plus a height squared equals a hypotenuse squared, or the radius squared. So now the radius of our circle is equal to 3, still with a center of 3, comma, -1. So every horizontal distance, which used to be the radius here, a horizontal radius and a vertical radius, it used to be 1, but it's going to be scaled by an amount of 3. And so we're going to go 1, 2, 3 to the right, 1, 2, 3 down, 1, 2, 3 to the left, and 1, 2, 3 up. Now imagine still a square. We can come up with our circle with a radius 3 centered at positive 3, comma, -1. Now this is actually really interesting because when we see dividing by 3, that sounds like multiplying by 3. And if we go back to this equation form, instead of the divided by 9, if we kept the 3 inside the brackets to be squared, we can rewrite this as 1/3 times x minus 3 all squared plus 1/3 times y plus 1 all squared, still equal to the 1 because we hadn't done the multiplying by 9. But now this multiplication factor is a scale factor, and there's one for x, so it's a horizontal scale factor, and there's one for y, a vertical scale factor. And from here, we know we are always going to do the opposite for transformations. So the horizontal scale factor is of 3, and the vertical scale factor is of 3, which is why we took the radius horizontally and vertically and multiplied by 3. Lastly, if we take a look at the purple equation, we see x minus 3 is being multiplied by 1/2, or divided by 2. And so we have 1/2 times x minus 3 all squared plus 1/3 times y plus 1 all squared equal to 1. So that actually gives us the same center and the same maximum and minimum points that we had from the green circle. But now we are no longer taking our parent circle, the blue one, translated to the red circle with the new center, and then taking this horizontal radius, we are only going to horizontally scale it by a factor of 2, whereas the vertical scale factor is a factor of 3. So we are only going to take the horizontal radius, if you will, 2 spaces right and left of the center. So now instead of fitting inside of a square, we have a curve that is fitting inside of a rectangle. And this curve then is an ellipse. And we would say it's a vertical ellipse because it's taller than it is wide. So at this point you might be asking the question, why do we do the opposite? And that's a really great question. So if we go back over here to this case, we can see what's happening when we consider the parent graph is the blue one, and we have the blue equation is y equals x squared, and the transformational form lines up underneath with red y coordinates. Y plus 1 is equal to x minus 3 all squared. Now I'm just going to put the plus 1 and the minus 3 in the squaring in a different color, because really the blue x and y is a point on the blue graph, and the red x and y represents coordinates of a point translated by the same vector to a new point on the red graph. But it's important to note that the blue x and the red x are not the same x's, and the blue y and the red y are not the same. However, if we make some alignments here, we can see that the blue y has to match up with the red y added to 1. And so blue y is equal to red y plus 1. Similarly, we have that the blue x is equal to the red x subtract 3. And so what we're seeing is that the direct instructions of subtracting 3 to x, which is the opposite of moving 3 spaces to the right, those direct instructions of subtracting 3 are the instructions we do to the red x to get the blue x. So those would be the instructions to go from the red to the blue. So if I were starting with the red graph and I wanted to go to the blue graph, I would be going 3 to the right, and then I would be going from the red y coordinate, I would add 1 to get the blue y coordinate, which means that to go from the red to the blue, my vector would be negative 3i hat plus 1j hat, according to the instructions on red to get blue. But the whole idea about the parent functions is that they're very easy to graph. They're basic. There haven't been any significant changes. And so the parent graph is what we want to start with. So we don't want the negative 3i hat plus j hat vector. We want the anti-parallel, or the reverse vector, the one that was in gold over here. And so what we're really doing is isolating for the thing we want to solve, the new x and y, the red x and y. So the red y is equal to the blue y, subtract 1. Meanwhile, the red x is equal to the blue x added to 3. And so now, considering that we're starting with the parent x and y, the instructions of adding 3 is consistent with doing the opposite, moving 3 spaces to the right, and the instructions of subtracting 1 from the blue y is how we go 1 space down. And so from this point of view, we realize going from the parent function to the new function is opposite the instructions that are given in the equation for the red graph. So this is why we always do the opposite. And I like doing the opposite for both because we cannot always isolate the y, which means sometimes if the graph is a curve, which is not a function, like a circle fails the vertical line test, we can't isolate the y. Therefore, keeping all of the transformations for y together, for x together, is consistent and it allows us to grow to more complicated graphs. So I'm going to pause this video here, and then I'm going to create a part 2 where we look at some parametric curves to see how we can apply these transformations combining with the parametric form. That's all for now.